Good day, everyone. This is Group 3. Today we'll be discussing the stability information, SOLAS Chapter 2-1, and focus tayo sa stability booklet. And in this presentation, we will be diving in the purpose of booklets, mga nilalaman nito, and we also be tackling the example calculations down this presentation and daily operational use, and last will be the accident case study.
Stability booklet definition. The stability booklet is comprehensive documented approved by the Flag Administration containing detailed information about the ship's stability, characteristic, purpose. It provides the master with the necessary guidance to operate the ship safely under the various loading conditions. The contents: general arrangement plans, hydroelastic curves, cross curves of stability, loading conditions, permissible kg curves or GM limits, damage stability information, loading instruments information. This is the key consideration for using the booklet. Understanding the data. The master and officers must be truly familiar with the contents, the stability booklet, and understand how to interpret the data. The stability booklet is an indispensable tool for ensuring the safe operation of a vessel. By understanding and adhering to the information contained within, we can minimize the risk of stability-related incident and protect lives, cargo, and the environment. Ensuring SOLAS compliance. Intact and damaged stability. The stability of the ships complies with the International Convention for the Safety of Life at Sea. The regulation for both intact and damaged stability. These regulations are in this place to confirm that a ship can withstand certain conditions without capsizing or sinking even if the hull is breached. Regulatory requirements. SOLAS Chapter 2-1 mandates that every ship has a stability booklet approved by the Flag Administration, which contains succession information to enable the master to operate the ship in compliance with the applicable requirements contained in the code. Master reference for stability characteristics. Comprehensive information. The booklet acts as the primary reference for the ship master regarding its stability characteristic across all potential loading conditions. This is some example of guiding safe operation planning tool. It guides officers and planning safe loading, ballasting, and cargo operation, ensuring the ship remains stable throughout these activities. Loading condition. The TS book should provide the following types of information: maintaining freeboard and reverse buoyancy, survivability. By adhering to the guidelines in stability booklet, the crew can maintain adequate freeboard, the distance between the waterline and the deck, and reserves buoyancy, the volume of the waterline part of the ship above the waterline. This maximizes the ship's survivability and adherence conditions. Supporting stability assessment, decision making, rapid evaluation, damage control. Contents overview, loading condition, kg, GM, trim, ballast, free surface effect. Overview of the key contents. A stability booklet contains critical information for safety operating a vessel, including loading conditions, kg, and GM values, trim and stability guidance, and explanation of the free surface effect. The booklet acts the primary reference for the shipmaster regarding its stability characteristic across all potential loading conditions. Loading conditions. Definition. This defines specific scenarios detailing the distribution of cargo fuel, water, and other weights. Purpose. Loading conditions are designed to ensure the ship meets stability criteria for various operational phases, such as departure, arrival of specific cargo configuration. Contents. Each loading condition includes a profile and plan view with color code with distribution for items like cargo, freshwater, and ballast. kg and GM. kg, vertical center of gravity. This is the height the ship's center of gravity above the keel bottom of the ship. A lower kg generally improves stability. Jm, metacentric height. This is the distance between the center of the gravity and the metacenter M. It indicates the ship's initial stability. A higher Gm provides greater initial stability but can result uncomfortable. Importance: the stability booklet specifies maximum kg or minimum Gm limits for differential drops to ensure compliance with stability regulation. Trim and ballast. Trim refers to the difference between the forward and aft draft. Proper trim essential for efficient propulsion and stability.
Loading conditions. Loading conditions are standardized vessel state defined by a ship combination of draft, trim, displacement, and weight distribution under specific cargo, fuel, and ballast arrangement. They serve as benchmark for evaluating and planning vessel stability performance. Common load cases: lightship, empty hold, minimal fuel; ballast, tank, fuel, full, no cargo; partial load, cargo, fuel part loaded; full load, maximum cargo and fuel. Loading conditions are different ways a ship can be loaded depending on how much cargo, fuel, water, and ballast it carries. These conditions are important because they help us understand how the ship will float, balance, and move safely in the water. There are common load cases that serve as guides. Lightships means the ship's empty with only a little fuel. Ballast means there is no cargo but the tanks are filled with water to keep balance. Partial load means the ship is carrying some cargo and fuel but not fully loaded. Full load means the ship is carrying the maximum amount of cargo and fuel. By knowing this loading condition, we can check the ship stability and make sure it is safe and ready to sail.
Kg and GM. The basics of stability. This slide defines Kg and GM, which are crucial for a ship's balance. Kg is the vertical distance from the keel bottom of the ship, labeled letter K, to the center of gravity, labeled letter G. GM is the metacentric height calculated as Km minus Kg, where M is the metacentric, a point above G that helps the ship right itself when titled. Bottom left, a cross-section of a ship's hull in water. Lines connect K to G to M with B for buoyancy center. Arrows show force like weight downward and buoyancy B upward. A low G means large GM, making the ship tips. It rolls quickly but uncomfortably. High G means small GM, making it tender, slow rolls but risks for capsizing if unstable. Risks include large GM causing violent rolls or small GM leading to flips. Why it matters? This measure prevent accident, for example, overloading cargo, high up rises G, reduce GM, and increase capsize risk. In real life, crews calculated this before sailing to ensure safety. That's about stability from gravity and buoyancy, like how a toy boat ships but is strengthened. Trim, balancing from front to back. This is lights cover trim, which is how level a ship sits lengthwise. What it shows? Title trims. It defines trim as the difference between forward bow and aft astern draft. how deep the ship sits at each end. Diagram show two ships, one trimmed by stern, stern lower bow up, stern lower bow is up, from weight added aft, crossing trim by stern, the other trim by head, bow lower from weight forward. Left side least wide trim matters, affect propeller immersion for speed, fuel, efficiency, cargo access, and operations. Bad trim can slow the ship or make it unstable. Right side notes, risks like large GM leading to steep and uncomfortable rolls. Ships aren't always even loading cargo or fuel. Ships wait, for instance, adding weight aft, trims by stern, which might help in shallow ports but hurts speed. Proper trim saves fuel and prevent issues like propeller exposure in waves. Think of it as balancing a seesaw. Uneven weight makes one end dip, affecting the ride. This connects to everyday boating. If your kayak tips forward, you adjust by shifting gear. Ballast and free surface effect. Purpose is to adjust draft, depth in water, trim and stability. Double bottom under floors, 4 wing front sides, aft wing back sides. Fill bottom first, then 4, then aft to hit target depth. Top right, small ship cross section showing tanks filling or emptying. Free surface effect, a yellow diagram of a partially filled tank. Liquid slashes when tilted. Shifting the center of gravity G to G1, creating a wedge that reduces stability. Free surface effect is stability loss from liquid moving in half full tanks, like water slashing in a bucket, making it easier. Why it is important? Ballast add weight, low down to lower gravity and boost GM. But partially tanks cause slashing, worsening rolls. Fill or empty tanks, fully or use dividers. In practice, tankers use ballast when empty to avoid floating too high and becoming unstable.
Okay, let's walk through a sample calculation para maintindihan natin paano mag-load ng cargo and paano ito nakaka-apekto sa ship's center of gravity. Okay, we're given the following. Lightship, which is nag-weight siya ng 8,000 tons na may kg of 4.8, and then we're gonna load a cargo of 4,000 tons at place siya with a kg of 6.5 liters. First, kakalculate natin yung total displacement. 8,000 tons plus 4,000 tons equals 12,000 tons. Tapos doon, we find the total moment by multiplying each weight dun sa kg niya, which this one is 8,000 multiplied by 4.8 is equals to 38,400 ton meters. Then next, yung cargo naman, which is 4,000 multiplied by its kg na 6.5 is equals to 26,000 ton meters. After that, i-add natin sila together, which is 38,400 plus 26,000 is equals to 64,400 ton meters. Now, para mahanap natin yung kg, we divide the total moment by the total displacement, which is 64,400 divided by 12,000 is equals 5.37. So, pagkatapos natin i-load yung cargo, yung ship's kg natin is increase from 4.8 to 5.37 meters. So, since the cargo was loaded at a higher kg, yung ship's center of gravity natin is tataas. At ito yung nagre-reduce ng initial transverse stability natin. At this makes our vessel more sensitive to rowing. This example shows paano ka-importante i-monitor yung ating kg. Lalo na when it comes to loading and dealing with heavy or high place cargo. Okay, for the next sample solution is for looking for the GM. To calculate the GM, yung metacentric height, we are given two values. First, km is 7.90 meters. Ito yung distance from keel to the metacenter. Tapos, next is yung kg, which is 5.37. Yun yung vertical center of gravity. Para mahanap yung GM, we use the formula GM is equals to km minus kg, which is 7.90 minus 5.37 equals 2.53. So, the vessel GM is 2.53 meters. And a positive GM, meaning yung vessel natin is merong good initial stability. At 2.53 meters, it will resist small angles of keel effectively. Pero, it may feel a bit stiff in roll motion, meaning, mag-return naman siya upright position niya, pero rough siya, sharper movements. This sample calculation shows that how GM help us assess the ship's behavior, especially during loading and cargo operations. So for the third sample calculation, hanapin naman natin yung trim change. And let's see how shifting of weights affects the vessel's trim. So sa given natin, meron tayong weight of a cargo of 450 tons, which is moved forward by a distance of 18 meters. So the vessel's moment to change trim per centimeter is 150 per centimeter, 150 tons per centimeter. To calculate this, we use the formula trim is equals to weight multiplied by distance divided by MCT per centimeter. So, meron tayong 450 multiplied by 18 divided by 150, which is 54 centimeters. So, yung vessel natin is may trim of 54 centimeter by the bow. This forward trim shifts the balance. Dahil doon sa cargo na forward, na-shift yung balance ng vessel natin towards the bow, which caused the bow na mas bumaba. Naapektuhan nito yung propeller immersion. Mas mahirapan yung propeller natin umandar. May increase din yung hull resistance, and ultimately, maglilid to sa higher consumption ng fuel at marireduce yung speed natin at the same time. And these samples calculation shows that how even a single weight can shift the impact performance.
Example calculation. This example is about finding how much ballast or extra weight a ship needs. Right now the ship's draft, which means how deep it in the water, is 7.00 meters. But the target draft we want is 7.50 meters. That means the ship needs to go deeper by 0.50 meters or 50 centimeters. We are also given TPC, which means tons per centimeter. Here it is 30. This tells us that for every 1 centimeter the ship goes down, it adds 30 tons of weight. So if the ship needs to go down by 50 centimeter, we multiply 50 by 30. The answer is 1500 tons. This means the ship must and 1500 tons of ballast so it can reach the correct draft. This is important so the ship stays balanced, safe, and ready to travel.
Here we have an example calculation for the free surface effect. We are given two values, the free surface moment, which is 2,000 ton-meters, and the ship displacement, which is 20,000. The formula is very simple. Gm due to free surface equals FSM divided by displacement. So when we divide 2,000 by 20,000, we get 0.10 meters. This means the ship stability or GM is reduced by 0.10. This is why officers must always include this correction when checking stability. The ships become slightly less stable because of liquid sloshing inside the tank. When liquid inside the tank moves or sloshes, it reduces the ship stability. In this case, the vessel stability is reduced by 0.10 meters. That means the ship becomes less stable, but this must always be considered to keep the vessel safe. So in real life, this free surface effect has played a big role in some major maritime accidents. For example, the Herald of Free Enterprise accident and another case in the MS Estonia. So these cases remind us that even a small reduction in GM, like 0.10 meters in our calculation, can be dangerous if ignored. That's why officers must always consider free surface effect when assessing a ship's stability. Daily operational use. Every day, ship operations focus on keeping stability safe. First, in cargo loading approval, we make sure the cargo plan follows the rules and that weight is balanced properly. Next, in ballasting, we fill our empty tanks to keep the ship's draft and trim correct while avoiding free surface effects. For the fuel and GM management, we track fuel use, update stability after bunkering, and shift fuel between tanks if needed. Finally, in emergency checks, we do quick stability tests and take immediate actions like moving cargo or adjusting ballast if stability drops. This step ensures the safety of the ship and stable throughout the voyage. Accident Case Study. Roro Ferry Stability Failures Case Study 1. Herald of Free Enterprise. Case Overview. Passenger Vehicle Ferry Capsize of Seabridge, March 1987. Stability Data Failures. Bow left open on departure, allowing car deck flooding. Free surface effect from floodwater not included in stability book calculations. No post-departure GM reassessment by crew. Consequences: rapid loss of righting moment, vessel heeled over in minutes, 193 lives lost, SOLAS amendments, cross-flooding requirements, tougher damage, stability rules, tighter control of watertight doors. So in this case study 1, this was a passenger vehicle ferry that capsized shortly after leaving the port. The bow doors were accidentally left open, which allowed the seawater to flood on car deck. Once the car deck flooded, the free surface effect reduced the ship stability quickly. The crew did not reassess the stability condition after departure, which was a critical mistake. Because of these failures, the ships lost stability and capsized in just a few minutes. As a result, 193 passengers and crew lost their lives. After this incident, SOLAS introduced stricter rules on cross-flooding system, damage stability, and control of watertight doors. So in case study 2, MS Estonia 1994 in Baltic Sea. The MS Estonia was a Roro ferry that tragically sank during a voyage in the Baltic Sea. The bow visor and ramp locks failed during rough weather, which allowed seawater to enter the car deck. The stability assessments did not fully account for the effects of water flooding inside. There was no real-time stability monitoring system on board to help the crew during the emergency. As a result, the ship lost stability and sank, killing 850 people, making it the worst peacetime maritime disaster in Europe. This tragedy led to new regulations such as stronger Bobbisor's lock, mandatory water ingress alarms, and stricter safety management standards.
So in conclusion, vessel stability is not just a technical requirement, and it's a foundation for safe and efficient maritime operations. Through our examples, we've seen how loading cargo affects the ship's center of gravity, kg, how GM reflects initial stability, and how shifting weight influences it. Each calculation highlights the importance of understanding and applying the principles found in Stability Booklet, as required by SOLAS Chapter 2-1. Whether you're managing ballast, planning cargo operations, or assessing trim, these tools help ensure the vessel remains safe, seaworthy, and compliant. As future maritime professionals, mastering stability isn't just about passing exam. It's about protecting lives, cargo, and the ship itself. Thank you for your attention, and we hope this presentation helped make stability concepts clearer and more practical.
Sometimes there's no one else who loves me like you used to. Sometimes